me, although I'm not sure I will see your hands raised. So someone will have to let me know if there is a question. Thank you, Chris, for inviting me to give this virtual talk. I will talk today about the dynamics of very large earthquakes, and in particular, what controls their rupture arrest, hence the rupture size, and what controls their rupture speed. And most of this work is the results from the work with Hui Wang, who has been a postdoc here in Jersey for the last 2 years and a half. Before I start, I want to acknowledge the sources of funding for this work and all the resources that our Université Côte d'Azur provides for this work. And as you can see, it's a wonderful place to be locked down. Here's an overview. I will essentially today talk about theoretical aspects of these two questions here: what controls the arrest of very large earthquakes and what controls their rupture speed. And some definitions, what I mean by very large earthquake is a rupture whose length is much larger than its width. The width is the depth extent of the rupture. And why this is important and relevant, if we look at this figure on the right, it's the slip distribution inferred for the 2004 Sumatra earthquake. And you can see that the aspect ratio of the rupture, the ratio of length to width, is very large. And this is often the case for large earthquakes because the ruptures eventually break the whole seismogenic depth. And from there on, they propagate horizontally. If we look at this figure in the middle, it's a compilation of aspect ratios for many earthquakes as a function of their magnitude. And you can see that the larger ones are also managed to develop these very large aspect ratios. And this is not only the case for very large earthquakes, it also can happen for smaller magnitudes. Here's the A dynamic model of the 2004 magnitude 6 Parkfield earthquake. And this dynamic model is consistent with some of the observations, recordings of this earthquake. And you can see that it has a very small depth extent compared to its lateral extent. So a high aspect ratio for a magnitude 6. And even here in France, recently, we had a magnitude 5 earthquake. It was in 2019, which was very shallow, but broke the surface. So the hypocenter was at 1.5 kilometers deep, and the rupture of the surface was about 4 or 5 kilometers large. So also a relatively large aspect ratio between 3 and 4 for such a small magnitude. Another reason why earthquakes with long aspect ratio can happen, it's not only those that break the whole seismogenic depth, but also those that remain confined at depth can develop large aspect ratios. And one reason for that is that one way in which faults are loaded is by creep in the deeper parts of the fault. And this tends to generate a stress concentration close to the transition between the locked part of the fault and the deeper aseismic creeping part. If we integrate that into earthquake cycle models, we often find this type of ruptures. So the blue area here, we're looking at the fault plane, and the blue area is what's creeping. The black area is the locked part of the fault, and an earthquake just happened in this simulation. And the rupture is basically this yellow area here. You can see is that this particular earthquake broke along the deeper edge of this transition between the locked zone and the creeping zone. This is a result of this stress concentration here near the bottom. And this also happens in nature. That's exactly our interpretation of what happened in the 2015 in the Gorkha earthquake in Nepal. And here we see the distribution of slip in red and pink colors. The surface trace of the fault is here. And this is a fault that's tipping towards the north. And this earthquake rupture, as you can see also in the sketch on the right, only broke the deeper part of the seismogenic zone and developed a large aspect ratio. So these things happen in reality for large and also moderate sized earthquakes. Something else I wanted to emphasize is that today I'll be focusing on theoretical aspects of these two problems. I will, of course, show you some of the observations that motivate the work, but most of the results I'll show are from theory and simulation. And today we have the capability to run very complicated, sophisticated 3D rupture dynamics models. And here's one example from a dynamic model of the Kaikoura earthquake in New Zealand in 2016. This is a model developed with Alice Gabriel's team. And it's a good example of what the sort of sophisticated simulations that we can do today. These simulations are expensive and they are complicated. So one way to try to understand the outcomes of very complicated systems is to use theory and simplified models, hoping that the analytical insight we can get from those simplified models can help us understand processes that are much more complicated, like this rupture that broke several fault segments at the same time. Of course, all models are wrong and some are useful, right? There's a saying about that. Here, what we're trying to do is find some shortcuts through problems that are highly complex. And that we're trying to understand the outcomes of these complicated problems by looking at elementary pieces of the problem. Of course, we cannot be so pretentious to hope to go from point A to point Z, which is one simple equation, right? But I hope that the results I'll show you today are a step, at least an intermediate step, to solve part of these complicated problems. So let's start with this first question: what controls the arrest of very large earthquakes? And this is a question that has to do with the final earthquake size. Here's a map of seismicity in South America. And we are going to focus on my home country here, Peru. We're looking at now the time and space distribution of the seismic activity in Peru. And we can look at this central segment. The seismicity organizes itself by segments. And for example, in the central segment that is separated by the Mendaña fracture zone that is subducting and the Nazca Ridge that is subducting in the south. Some earthquakes have broken part of this segment. Some larger earthquakes have broken almost the whole segment. But no earthquake in the past has managed to break across the two barriers that delineate this segment here. So some of the questions that we would like to understand better is there any chance that an earthquake in the future runs across one of these barriers and hence becomes bigger than what we have seen in the past? Are these barriers permanent or temporary? Today, we have also information from GPS data that can be used to infer these coupling maps. Is what we see in the right. It's a map that tells us at what rate is the sleep deficit being accumulated in the subduction megathrust. And the red parts of this map tells us what are the places where sleep deficit is accumulating fast. And if we multiply this deficit rate by the time since the last large earthquake, we can get an estimate of how much sleep could the next earthquake release at any point on this map. But what this doesn't tell us is the following. If we assume that an earthquake starts somewhere in this map and releases the amount of sleep that we see here, how large can that rupture break? So that is still something that is not easily portrayed by these coupling maps, and that's something we want to develop theory for. So the basic first question here is, what can rupture dynamics theory tell us about earthquake sizes in segmented fault systems? And the practical impact of this is, can we use these theoretical arguments to complement or improve the way we do seismic hazard assessment? The initial results about this were published in JGR in 2019 by Hui Wang. The starting point is fracture mechanics. Fracture mechanics is all about energy balance close to the rupture tip. Before the rupture starts, there's a certain amount of elastic potential energy, we call it G0, that is stored in the rock that surrounds the fault. And during rupture, part of that energy will flow towards the rupture tip, that one we call G, the energy release rate. And then the other part of the energy will radiate away via seismic waves. That's the radiated energy. The energy release rate, the former, is dissipated at the rupture front in the form of what we call fracture energy, which is just the amount of dissipated energy. It can lump frictional dissipation, but also any other process that happens close to the rupture, not necessarily on the fault. It could also include inelastic deformation outside the fault. So fracture energy, we call it G sub C. And maybe 30, 40 years ago, it was very well established that a very fundamental result of fracture mechanics was established in which we call the crack tip equation of motion. Let's consider a circular rupture. And if we write this energy balance of the rupture tip, fracture energy is equal to the energy release rate for a rupture that propagates at a speed r dot. That's the time derivative of the size of the rupture, which can be variable, okay? It's a non-steady rupture. We can write down that equation in the following form. It involves on the left-hand side the fracture energy, a known function of rupture speed, a stress rup, just that squared, the radius of the rupture, and twice the shear modulus of the surrounding rock. And if you pay attention to this equation, here the unknowns are the time dependence history of the rupture size, R of T. And we can rewrite this equation in the form of an ordinary differential equation. Time derivative of size equals a function of size and some other things, some other quantities that we can assume that we know them and how they are distributed along the fault. If we know that, if we know how the fracture energy, for example, is distributed along the fault and how the initial stresses are distributed, we can solve this equation to get the full history of the growth of the rupture. So that was a fundamental result in fracture mechanics that is more than 30 years old now. And it has been very useful for us to understand several processes at the laboratory scale and also at natural scale. So I'll just give quickly two examples here. There's a laboratory experiment by Jay Feinberg's team pushing into a block that slides over a surface, a frictional surface. And as you increase the force that pushes the block, the sleep starts by small events that don't break the whole interface, but only partly. And you keep increasing and events larger and larger will happen. So here's a figure showing the activity of sleep on that interface as a function of distance from the loading point and as a function of time. And each horizontal bar is one sleep event. These are partial events, and at some point, critical size is reached, beyond which the rupture will just break the whole interface. And by using fracture mechanics and by realizing that the load imposed by this point load is concentrated, it's higher here close to the loading point, we managed to explain the laboratory results about the history and the sequence of the sizes of events that produced in this laboratory experiment. And this was interesting to us because up to that point, physicists had been wondering a lot and proposing a lot of original models to try to explain these observations. And just fracture mechanics is sufficient to do so. We have used also this fracture mechanics theory of rupture arrest for circular ruptures to come up with scaling relations for induced seismicity. Here's, for example, the maximum magnitude of induced earthquakes plotted as a function of the net injected volume during injection operations. Here's the data for induced earthquakes. There's also data from underground lab experiments and data from laboratory experiments. And if you look at the overall trend, it is actually consistent with the prediction that we can make by using fracture mechanics applied to this situation where you trigger a rupture by a concentrated load due to pressure injection. And some colleagues have gone one step beyond, is to use in real operations those scaling relations to extrapolate or to forecast what could be the consequence of keep injecting and then being able to stop their injection operations before a certain regulatory threshold on trigger, on induced magnitude was reached. So that was a success story in Helsinki in Finland. So here we have this classical theory that has been pretty successful so far. But large earthquakes have large aspect ratios, and that's not something that was contemplated by the previous theory. Here's an example of a dynamic rupture simulation on of a long rupture. And what you can see here is that at the beginning, we have a circular front, but once the rupture saturates the whole seismogenic width, it starts propagating bilaterally as two pulses that propagate horizontally. So we have here naturally a transition from a circular rupture to a bilateral pulse-like rupture. And that changes the energy picture dramatically. How do we know that? If we look at a circular rupture, the energy release rate is proportional to the radius of the rupture. For a very long rupture, well, now you have two length scales in the problem, the length and the width. And it turns out that the energy release rate is proportional to the width. And this is an important difference because for a circular rupture, the energy release rate keeps growing with time as the radius of the rupture grows. But that is not the case for a long rupture. It doesn't keep growing with length, it saturates with the rupture, the seismogenic width or the rupture width. So we try to get inspiration from previous situations that had been studied in fracture dynamics, in particular situations that involved also a additional length scale. So here's one that was very important. This is a crack, a fracture that's propagating in the middle of an elastic slab that has a finite width W. In this particular case, the static energy release rate is proportional to the width, not to the length of the rupture. Moreover, there was this theoretical paper by Marder in 1998, where he established, under some assumptions and approximations, a new crack tip equation of motion for a rupture in this configuration. And it is a very interesting one because it not only involves the rupture speed, but also the time derivative of the rupture speed, the rupture acceleration. So that basically introduces in the equation of motion of a crack an inertial term. And we call it inertial because it looks like a mass multiplied by an acceleration. It's rupture acceleration. So that's very interesting. It has this, this form that we can rewrite it in this F equals ma form here. All right, so what we did is we took, we did a lot of 3D dynamic rupture simulations like the one you see at the bottom, in which he started with more or less energy in the system. So cases with larger potential energy than fracture energy, or the other way around. And for each simulation, we looked at how the rupture speed evolved along the rupture as a function of rupture distance. And we were able to fit to this numerical results an equation that was similar, or our adaptation of the equation that had been established by Marder for that other problem. Then we did one more step, which was trying to simplify the 3D problem into what we can call a 2.5D problem. So if this is one simple form of the elastic wave equation in 3D, we considered that sleep was distributed as half a sinusoidal function, as a function of depth. And we plugged that into the equations and simplified one of the terms and eliminated the depth variable in the equations to obtain a 2D equation that looks like the wave equation, but has an additional term here that introduces or encapsulates the main ingredient, which is the finite seismogenic depth. So this is now a 2.5D equation, and that has two advantages. One is that it's computationally much less expensive than a 3D problem. So we can run a lot of simulations in 2.5D. And it's also amenable for analytical work, so we can derive some equations for this problem. And that's what we did. We derived forms of this crack tip equation of motion, which we tested, and so you can look at the JGR paper for more details about that. It's interesting that, okay, here's the equation of motion, very similar to that one developed by Marder. It contains two quantities that may depend on position along the fault. One is on the left-hand side, the fracture energy. So fracture energy can change along the fault because normal stress changes, or because the material changes, or there's different materials that are being subducted, and so on. And on the right-hand side, we have also the potential elastic energy that may vary along a strike because the initial stresses might be lower or higher in different places of a fault. So it is the balance between these two terms. So in this sketch, we have pictured one of the terms, the potential energy in blue and the fracture energy in black. In areas of a fault where there's more potential energy than fracture energy, the rupture will tend to accelerate, and the opposite will happen in places where the fracture energy is large enough. So we can solve this equation in situations where both quantities are heterogeneous, and that would lead to transient histories of rupture propagation that we can compare to the numerical simulations. And that's what we did in this paper. And you can see from the agreement in the picture on the right-hand side, where we have a plot of rupture acceleration as a function of rupture speed. In red are the numerical results, and in black are the theoretical predictions. So there's a good predictability in these simulations, both in 2.5D and in 3D. So the outcome of that work was this crack tip equation of motion that can then serve us to develop some implications for rupture arrest. So basically, if you know the quantities on the left-hand side, you can solve this equation to obtain the history of the ruptures. One implication is a dramatic difference between the 2D theory or the circular crack theory and the 3D theory of long ruptures. What happens when a rupture hits a barrier? That's a region with very high fracture energy. In the 2D theory or in circular crack theory, as soon as a rupture hits the wall, boom, it will stop immediately. But that is not the case in the theory of long ruptures. A rupture will hit the barrier and will penetrate a significant distance. So the strength of barriers is quite different in 2D and 3D. We can manipulate this equation of motion in a way to define what we call a rupture potential. I'll skip the details of the derivation. The rupture potential is a quantity it's an integral of 1 minus the energy ratio between fracture energy and potential energy. If we have, if we know the distribution of these two quantities along the fault, we can compute this rupture potential, and there's an example here. And it acts a little bit like a gravity potential for a roller coaster, for example. If the hypocenter is located here at this particular point of the rupture potential landscape, the potential helps you predict where the rupture will stop. And it will stop at the points where the potential reaches again the value that it had close to the hypocenter. Now, in this rupture potential, if you keep waiting more time and you let the tectonic stresses build up, the potential energy G0 will increase. The rupture potential will change and maybe reach this other situation here of the darker gray curve at the bottom. And now if you trigger, or if an earthquake starts at the same point, it will be capable of growing even larger. Now, because the points of same value of the rupture potential have extended to further regions. And in this way, you can envisage how an earthquake cycle could happen with early on in the earthquake cycle, capability of breaking only part of a fault, and later during the cycle, increasing probability of breaking the whole fault segment. So how do we estimate this energy ratio here that appears in the energy potential? So there's two parts of it. There's the potential energy G0 and the fracture energy. So let's start with the first one. We can try to get estimates of that from the coupling maps that are inferred from GPS. So this is a sleep deficit map. If we look at the expression for the potential energy, if the width of the seismogenic zone is fixed, we know the shear modulus of the rock, then the remaining unknown is the amount of stress that can drop during the earthquake. And this, using elasticity relations, is proportional to the square of the sleep deficit that has been accumulated since the last, since the previous large earthquake in the region. Okay, so this from a coupling map, by integrating across depth the sleep deficit rate, multiplying by the time since the last earthquake, we can get an estimate of potential energy. What about the fracture energy? Well, this is a big unknown, right, in earthquake mechanics. There's one avenue to get an observational constraint on that is from work like the seminal work by Viesk and Garagash. They compiled seismological estimates of fracture energy as a function of sleep. And they even compare that favorably to some theories of thermal weakening. And what comes out of these and similar papers is that you can probably postulate a power law relation between fracture energy and final sleep. In this particular case, we can fit this by an exponent of 0.7. So we can now combine these two pieces of information and to compute a potential, earthquake potential for any region. And here it shows the area of the Maule earthquake, I think, in Chile. And the figure on the right shows as a function of latitude and as a function of the time that has been elapsed since 1960. Sorry, it's not the Maule earthquake, it's the big 1960 earthquake in Chile, Valdivia earthquake. What this black curve in the figure separates is two areas at early times, areas where the available energy is not sufficient to nucleate a runaway rupture, and at later times, the areas that can nucleate runaway ruptures. These are self-sustained ruptures that can propagate in a substantial part of the fault. And this allows us to make some predictions about how ready is a fault to break in large or larger or huge earthquakes as the time passes. Of course, there are uncertainties on all these quantities here. So I'm showing this more as a concept or something that could be useful as in the future we try to narrow down the uncertainties in these quantities here. Or it also shows us which quantities are important and need more work to reduce their uncertainties to be able to say something about the sizes of future earthquakes and how hazard evolves with time. All right, so for this first question, the conclusion so far is that we introduced a 3D theory of long rupture dynamics that provides a new theoretical basis for that we can hope to use for hazard assessment. And we have ongoing work, taking coupling maps from different areas around the world and trying to validate and calibrate and test this model. Let me now move on to the second question, which was what controls the rupture speed of large earthquakes? And before I start, I wanted to say a couple of words in memory of Joe Andrews, who unfortunately passed away recently. And he was a pioneer in computational and theoretical earthquake dynamics. He was a major contributor to many topics in earthquake science, in particular the topic of rupture speed that I will cover now. And his work has been extremely influential for my own work and for many people in my working on theoretical and computational earthquake dynamics. So thank you, Joe Andrews, for all your seminal contributions to rupture dynamics. Earthquakes, the simple analogy of a point source, that works pretty well for small earthquakes, but for large earthquakes, we really need to account for the finite size of ruptures, and earthquake sources are moving sources. And the fact that they are moving, like this ship here in the water, leaves patterns in the wave field that are very interesting and that have actually impacts on how strong it can be the ground motion, and how ground motion depends actually on how fast the source moves, which is the rupture speed. Here's our results from numerical simulations by Eric Dunham and Harsha Bhatt. They considered a simple earthquake rupture model where you have a pulse that is moving along a fault. And in the figures on the right, we'll be looking at the ground motions in 1/4 in map view and only 1/4 of the model. So, for example, in this figure here in the top right, the fault is located at the bottom of the plot. At this point in time, it has reached almost to position 15 along strike. And we're looking at the fault parallel horizontal velocity. And there's 3 simulations shown here, from top to bottom, increasing rupture speed. What you can see is that when the rupture speed is faster than S waves, there's a generation of a very sharp front here that carries very strong fault parallel velocity, very strong motion. And if you keep increasing the rupture speed, that becomes even sharper and stronger. So rupture speed, this shows how rupture speed can affect ground motion, and in particular, these speeds that are faster than S waves can generate a quite significant pattern. And this is completely analogous to the shock wave, that front that is produced by an airplane that goes across the sound wave speed. It will produce a conical wave pattern that has very sharp intensity. And that can be understood by geometrical considerations, as in this sketch in the middle. So these things were well known more than 10 years ago, and also something that was pretty well known was what are the admissible rupture speeds in 2D theory. For a deep sleep rupture that propagates horizontally, the rupture speeds that are slower than S waves are admissible, but not speeds that are faster than the S wave. They are forbidden in the sense that if you try to propagate a rupture at a steady speed, higher than the S wave, instead of energy flowing towards the crack tip, there will be energy flowing away from the crack tip, and that is inconsistent with our physical picture of the crack tip being a place where energy is dissipated. What happens for a strike slip fault that whose rupture propagates horizontally? It's a bit more complicated because now we have S waves and P waves that are important. So anything below the Rayleigh wave speed is admissible. So we call the subshear rupture speeds. There are speeds that are admissible above the S wave speed, even close to the P wave speed, not faster than P wave, but in between what we call the Eshelby speed, which is the square root of 2 times S wave speed, and P waves. Those are super shear admissible speeds. And there's an intermediate range plotted in yellow here between the Rayleigh speed and the Eshelby speed that is inadmissible or unstable. You cannot propagate a steady rupture in 2D at those speeds. It came the Palu earthquake in Indonesia a few years ago. This was one of the best observed and recorded super shear earthquakes. And using teleseismic backprojection analysis, we were able to determine the rupture speed of this earthquake. It was pretty steady along 150 kilometers of rupture, with a value that turned out to lie within that unexpected speed range. So this was very puzzling for us. It's also a rupture that has a very large aspect ratio, 150 kilometers long, and let's say it's a strike slip fault, so about 15 kilometers deep. So that's an order of 10 aspect ratio. So a good candidate to try to study with our theories of long rupture. Why did this earthquake run at that unexpected speed? And what does it take for earthquakes to run at unexpected speeds? What can 3D rupture dynamics tell us more generally about the rupture speed of large earthquakes? Some of the results that I'll show now are in the paper published last year in Nature Geoscience with Hui Wang, and I'll also show some more recent observational results and earthquake cycle modeling results by other colleagues, collaborators. So the ingredient that we considered here was the following. The direction of sleep in a natural fault is not necessarily horizontal or vertical. You can have anything in between. You can have oblique sleep. That's the angle theta here in this picture. We call that the rake. A rake of 0 is a pure strike slip fault. A rake of 90 degrees is a pure deep sleep fault, and anything in between can happen and does happen in nature. Hui Wang was playing with earthquake simulations as if it was his rock mechanics laboratory, and he was exploring the effect of rake on earthquake rupture. And here are results of a set of simulations. What is plotted here, each curve comes from one simulation. What is plotted is the evolution of the rupture speed during the simulation as a function of the distance of rupture propagation. And what we can see is that some of these ruptures accelerate, some decelerate, but they all sort of reach a steady rupture eventually. And interestingly, the ones that have within a certain range of rake angles, the ruptures reach a steady rupture speed that lies within that unexpected speed range. So that was the numerical result. One way of understanding this is that the strike slip faults can manage to propagate very fast at super shear speeds. For the deep sleep faults, we don't expect that. They can only be super shear, the pure deep sleep ones. And then when we put them together by oblique sleep, it's as if you had a slow runner and the fast runner running together. And the collaborative effect is to run at any speed in between the low and the high. And this, leads to speeds that lie in that intermediate or unexpected range. Of course, beyond these hand-wavy arguments, we can use energy balance to gain insight into why these unexpected speeds are actually admissible in 3D. Here's the energy balance. It does contain, now that the rake is allowed to be non-zero and non-90 degrees, it contains two terms. Theta is the rake angle, and speeds that are faster, slightly faster than Rayleigh waves, the term that is associated to strike slip rupture is negative, and this makes it inadmissible in 2D. But the other term, the term associated to deep sleep, is not negative, it's positive. And sometimes it is larger than the other term. So overall, the sum can be positive, even if one of these terms is negative. So basically, the different energy contributions of the strike slip and the deep sleep component combined together lead to admissibility of ruptures, speeds that were unexpected otherwise. This theory is explained in detail, of course, in the paper. An outcome of that is this phase diagram where we can plot all the expected rupture speeds as a function of the energy ratio on the horizontal axis. That's the ratio between fracture energy and potential energy. So it's the same energy ratio we discussed in the first part of the talk. And on the vertical axis, the rake and the obliquity of the sleep. At low rake angles, that's for pure strike slip faults, we can have ruptures that are self-arresting, they don't run away. We can have subshear runaway ruptures in blue, and then we can jump to fast super shear ruptures in red. For the pure deep sleep faults, we only have self-arresting rupture or subshear ruptures. And in between, for these oblique rake angles, we can go from subshear ruptures to all the unexpected range, which is here plotted in yellow and orange. So I should call it previously unexpected range, because now we understood why it is admissible.
Pablo?
Yes.
It's Chris. Just if you don't mind being interrupted for a second, can
Sure.
you say a little bit more about what constraints this puts on fault roughness or geometric complexity? Because I can picture that by, if you had a geometrically complex fault, you'd be changing this angle kind of continuously.
Oh, the rake angle. Yes. Well, that's a very good question. Here, everything here is a little bit macroscopic. So we're averaging over the whole seismogenic depth to do this theory. So I think a lot of the effect of roughness will have to emerge here. At least the small scale roughness, that's smaller than the seismogenic width, will have to be accounted for by other terms. So for example, the roughness drag, which is a resistance to shear stress proportional to sleep, is one way of representing the roughness effects. And the larger scale non-planarity of the fault, yes, that's something that we are still working on. We have started a project to look at how we can extend this theory to systems of faults that are not planar. And the goal is to make to propose physics-based predictions for the largest magnitudes that could happen in a gas field in the Netherlands, the Groningen gas field. So we're not there yet. Maybe in a couple of years and a year from now, I'll have a better answer to your question. Thank you.
Thank you.
Yeah, and Pablo, I have a quick question too. Is there data that shows the obliquity of the faulting matches this rupture speed?
Yes, and here it is.
Okay, good.
So here are the circles are come from estimates of rupture speed and rake angle from earthquakes and from different types of estimates. Some are from directivity analysis, some are from finite source inversions, and all of them have pretty large uncertainties. So let's look at the overall trend of this. What we can see here is that the rare earthquakes that have the speeds that seem to be in this unexpected range are also the ones that have larger or intermediate rake angles. So that would be something consistent with the theory here. As we improve our ways of estimating rupture speeds, I think we'll be able to narrow down this picture better. Here's one way we're trying to do that, and this is work led by Han Bao, who's a grad student of Ling Sang Meng in UCLA. And he did a quite comprehensive survey of ruptures, large earthquakes, larger than magnitude 6.7 in the past 20 years, using both teleseismic back projection analysis and surface Mach waves. That's one indicator of super shear on surface waves. And so far, he has found that 12 out of 83 earthquakes were super shear. So at least 15% of earthquakes are super shear. So that's an interesting number, an interesting target for future modeling, so for ongoing modeling. Why do we have only 15%? Why that number? So if we come back to this diagram here, and we try to look at this as a function of time, for a given fault, okay, let's assume the rake angle is fixed. So we will move, but the energy ratio can change through time, especially because the available energy, G0, is increasing with time. So as a function of time within an earthquake cycle, we will be coming from the right part of this diagram and will be moving horizontally towards the left. And as you move, as the time passes, you go from the possibility of only self-arresting ruptures, those are ruptures that don't break the whole fault, to runaway ruptures that can break the whole segment but are subshear, to faster ruptures that can have intermediate speeds or even fast super shear speed. So if during the earthquake cycle, there's the rate of nucleation of events is not frequent enough that you can pass all this time of the blue area without nucleating an earthquake, you will hit this yellow, orange, and red region where now super shear and fast rupture speeds are possible. So there's probably this delicate balance between the speed at which tectonic energy is being accumulated and the speed at which earthquakes are being nucleated that controls perhaps this probability of having super shear earthquakes or not. So now this can be studied through earthquake cycle models, and that's something we're doing more recently with Chao Liang, who just finished a postdoc here in my team and is moving back to China. He's got a permanent position there. He ran earthquake cycle models to address this question of what is the prevalence of super shear ruptures. And he has some initial results that we'll submit soon for publication. And in order to be able to do this, there was no way we could do this in 3D. 3D earthquake cycle models are very expensive. So fortunately, we had shown already that these 2.5D models are actually suitable to address this problem. We can account for the finite seismogenic depth at the cost of a 2D simulation. So he has been able to run many earthquake cycle simulations, changing, for example, the ratio of A and B parameters in the rate and state friction law, changing the ratio of the seismogenic width to the nucleation size, and mapping for all these combinations of parameters, how often do super shear earthquakes happen. And there's also some theoretical developments in his paper that will be interesting. So soon we'll have a preprint about this, and I'll welcome you to have a look at it. Okay, so I'll close here and conclude this. I think the important result I wanted to present today is that we have this new 3D theory of rupture dynamics that applies to long ruptures, those that are longer than wide. And it accounts for the finite rupture width and also for oblique sleep. Found that those two things are very important for large earthquakes. This gives us insights on rupture arrest, on rupture speed. The work also shows that 2.5D modeling is a very efficient way of studying large earthquakes computationally. And among the perspectives, the things that we're working on right now is extracting the implications of this for physics-based hazard assessment. We're working with colleagues that do laboratory experiments, design experiments that will test some of the specific predictions that we can do with this theory. And also looking at other natural earthquakes, types of sleep where we can hope to validate our predictions about rupture arrest. And one of those sources of data are actually slow sleep events, for which we have observed, for example, in Cascadia, tens of cycles, so more than tens of cycles. And so that's an excellent source of data to validate this. All right, well, I'll stop there, and hope you have some questions. Thank you.
Wonderful. I invite everyone to unmute and to turn their camera on if they'd like, and to join me in thanking Pablo for a fabulous talk. So.
Thank you.
Yeah, really great. So please take advantage of the reactions at the bottom of your screen. If you click on that smiley face guy right there, like Alan Rubin already knows how to do, you can ask a question. Alan, please.
Oh yeah, I was all set to click on him or her. Pablo, great talk. I actually have a question about the first part of the talk and the second part of the talk, and maybe I'll stick with the second part of the talk and then sign off and come back on if there's time. So in the simulation, you showed the 3D simulation with the oblique rake. There was a well-pronounced dip to the front of the rupture as it moved along the fault.